And thanks to the organizers for inviting me. Very nice to be here. All right, so I'm going to so in this talk I'm going to talk about some things which are motivated, can be motivated by features of the of omega logic and the omega conjecture. So that's the main topic. So I will start with this simple observation. So I'm going to talk about forcibility of sigma 2 sentences. And the sigma 2 sentence, so the first observation is that every sigma 2 sentences are the same thing as same as of the form, you know, there's alpha such as some V alpha satisfies sigma, and this for any sentence sigma, right? So if sigma is any sentence, then this thing is sigma 2, and any sigma 2 sentence is holds if and only if it holds in some V alpha. Okay. First thing I want to remind you of is a very nice, surprising early application of the stationary tower, which is a resurrection of sigma 2 truth. Okay, which says, suppose there's a result of Woodin. Suppose there's a proper class of Woodin cardinals, and sigma is any true sigma 2 state sentence, saying there's a rank to rank embedding. Then you do any forcing. So you make it, you make that rank embedding, say you collapse it to omega, and then there's a further forcing that resurrects it, right? And the proof is the following. So we start with an alpha such that V alpha satisfies sigma. Take a delta high enough Woodin cardinal, so above alpha and the size of P, and let G be generic for the full stationary tower. Okay. So you look at the full stationary tower, and you restrict it to this stationary set of all, you know, countable subsets of this thing, the power set of P. All right, so what that gives you is that in the extension, there's a generic embedding from V into some submodel M ascending delta to delta, and M is closed under less than delta sequences. So in particular, alpha is sent, you know, J of alpha is sent is something below delta, and M computes, you know, agrees with V of G about V of G alpha, and M thinks that this is the case, so this is the case in V of G. And finally, in V of G, there's a P generic filter G over V, since you made the power set of P in V of G countable. So, okay, so this is a regular extension of P, which resurrects your sigma 2 statement.
Right. There are too many P's.
Okay, yeah.
Pronounce the P.
Different forms, yes.
So this P or P is the power set of P, right?
Yes, yeah, that's the power set of P. Yeah. Okay, so Woodin's omega logic is a statement that is this strong logic that says, well, say you have a set T of sentences in the language of set theory. Now a sentence sigma, and then you say that T implies sigma in omega logic if any V alpha of any forcing extension, if it satisfies T, then it has to satisfy sigma. So it's an actual forcing of logic of forcibility, and this for sigma 2 sentences. So by the previous theorem, this is this relation, this logical relation is absolute modulo set forcing, okay, if you happen to have a property of Woodin kernel. So it's like first order logic in this sense. Now, okay, so Sandra talked about universally bare sets, so I can skip this. And I will give this, so Woodin proposed this calculus for this logic in terms of universally bare sets. So, okay, so he defines the T proves sigma in omega logic syntactically, if and only if there's a universally bare set A. So think of this A as some sort of proof of sigma, such that whenever M, such that M will satisfy that T implies sigma semantically, whenever M is a countable transitive model of Z of C, which is A closed. So here, M being A closed means that you take any set generic extension of M in V, right? And it's countable. You have plenty of them, and you look at the set of reals A intersection that the set of reals in A in that extension that belongs to M of G, and this for every set generic extension of M. So in practice, you'll be in a situation where being A closed for a suitable M means that M is sufficiently correct within V. For example, close on the sharps, or even sigma 1, 3 correct in V, or things like that. Okay, so you're saying that there is some notion of being rich or being correct, so that any M which is correct at that level will satisfy this state. Okay, so the sigma is more complicated. The more complex A is, that gives you this. All right. Now, if T implies sigma syntactically, so there's a proof, then T implies sigma semantically. So there's a soundness theorem, and the reason is, and this is very easy. So you prove the counterpositive. Suppose this fails. So then let A be universally bare as witnessed by trees as well. This part doesn't matter really. So let A be any universally bare set, and suppose that N is an elementary submodel of some H theta, which is large enough, which is countable and contains A. Now look at M, the transitive collapse of N. Then I claim that M. So for one thing, M will think that this is the case. But I claim that M is A closed, and the reason is that given any forcing in M, look at the anti-collapse of that forcing in N, and take any pair of trees that witness that A is universally bare set, and then look at the projection of S in M, and that will because you get a tree in that projection, then that really is in the projection of S. So the trick is having that N has trees witnessing universal bareness. So this is easy. So you have the soundness and the converse, which by the theorem above amounts to the completeness theorem. Omega logic says that these two relations are the same. That's known as the Omega conjecture. Okay, so you have this if and only if you have a proof in this sense. Okay, now if there's a if there's a proper class of Woodin kernels, then the truth value of the Omega conjecture is absolute modulo set forcing. That is the thing I want to mention. And also the Omega conjecture holds in all known canonical inner models for large kernels. Reason being that these inner models have iterable countable initial segments with universally bare iteration strategies. In fact, I'm going to now sketch a standard approach to proving the Omega conjecture. So how would you prove the Omega conjecture? Because I'll say something related to this approach. Okay, so here is the classical extender algebra approach to proving the Omega conjecture. So suppose that sigma is a sigma 2 sentence such that it's not provable. Okay, so that means for every UB set A, universally bare set A, there's some A closed and set N, such that N thinks that sigma is forcible. Okay, and you would like to show that sigma is forcible somehow over V. Okay, so that's proving the Omega conjecture. So now suppose that M is a transitive collapse of some sufficiently correct countable structure, right? And suppose that in M there's a Woodin kernel. And it will be enough to show that M thinks that sigma is forcible, right? Okay, now suppose, moreover, that there is an iteration strategy gamma for countable iteration trees on M, or suitable iteration trees on M, which is universally bare. This iteration strategy in the codes. This means that there's a UB set A of reals that codes this iteration strategies gamma seen as a function sending countable iteration trees T on M of limit length constructed according to the strategy to some cofinal well-founded primes through T. Okay, so there's this iteration game. where the bad player picks some extender and the least model where he or she can apply it, and the good player plays well-founded branches to the constructed iteration tree. Okay? And we want the good player to have a strategy that ensures victory. So moreover, this UB set has to be sufficiently, sufficiently independent. This coding has to be sufficiently nice in the sense that if you have two reals in A and they both code for the same tree T, they code pair T and the branch, then the branches have to be the same. Okay, so suppose that this is the case. That can be a big suppose. And then, so in that situation, if n is any model n which is A closed, then for every ordinal tau in n, there's in n an iteration strategy, like this for iteration trees on m of length this much, most tau. So this strategy is definable over n from any collapse name in n for this intersection, which exists, using the homogeneity of the collapse.
Yeah. So A become n in line 3, or it's
no, that's fine. So iteration is on n, right? So n contains m, and we will want to iterate m inside n.
okay.
Yeah. So now, by our hypothesis, I know that there's an A close n, which moreover, contains n, just by changing it slightly, and which thinks that n, so n thinks that sigma is forcible, right? So now you fix an ordinal in n such that its V alpha thinks that sigma is forcible, same, and then some set of ordinals in n that codes V alpha of n, and look at some high. Some high enough length, and now pick an iteration strategy for normal iteration trees of length at most tau in n. Now working within n and using this strategy, we can construct a normal iteration tree T on m of some success length, some alpha, such that when you look at the image of delta into the last model, look at all sentences find this infinitary logic. I'll clarify this in a moment in the next slide. In this model that satisfy A, that is generic over this last iterate for the image of some forcing, and this forcing is the extender algebra on delta with delta generators. Okay. So this, and this, I'll just say that this is it's a quotient Boolean algebra that you get by looking at this this propositional algebra of formulas in this infinitary language, where you have constant symbols for every psi being in the set you want to decide. And by closing under the usual connectives and also with infinite conjunctions and disjunctions of length less than delta. And then you mod that by the theory, some theory that says essentially that if you have a bunch of sentences, if this disjunction, if some of them, for some long enough eta, if some of them holds, then this has to reflect to some sentence below kappa, the critical point of some extender holding. Anyway, so and there are variations you can make of this. So anyway, this is a sort of well-known forcing due to Woodin. And now since A is in this extension, right? A was the set that was coding V alpha of n. Then this guy, can reconstruct this V alpha of n, and so it's contained in it. Now the crucial point is that since this construction was done in n, we in fact have that V alpha of n is equal to V alpha of this model. So, but now we're done, right? And now we're done because now we get the desired conclusion by elementarity of this J0 alpha embedding, because this guy thinks that sigma is forcible, as witnessed by G followed by whichever forcing lived here, forces state. Okay. So, this scenario for proving the omega conjecture, well, it's not a proof, it's a scenario for proving it, depends crucially on a strong iterability hypothesis on countable elementary submodels, okay? But now the first observation is that it turns out that we do get enough iterability for in V for elementary submodels of LV delta, and this for suitably fixed delta, so that we can actually prove the following result on a certain result on reflecting forcibility over V to that happening over L of V delta for some fixed suitable delta. And I wouldn't be surprised if this result or something like it has been observed already. Yeah, anyway, I mean, it was new for me and I think it's interesting. So, so here is the observational theorem that says, suppose there is a proper class of Woodin kernels and delta is an ordinal such that delta is Woodin in L of V delta, and the set of Woodin kernels in that model below delta is bounded in delta. Okay? So for example, if delta is the least ordinal, which is Woodin in the L of V delta. Right? Look at that ordinal. And now suppose that sigma is any forcible sigma 2 sentence. There's a rank-into-rank embedding. Then there's an ordinal alpha less than delta, and the partial order Q in the power set of V delta in L of V delta, unfortunately, such that L of V delta thinks that Q is smallish. It has the delta CC, and forces that that this sigma holds in V alpha. Okay, so of course you're not forcing over V. I mean, that will give you the omega conjecture, but you're forcing over L of V delta. Okay, so the proof of this the theorem is an adaptation of the previous scenario for proving the omega conjecture. So that's the first thing. So it's the extended algebra argument like that. Using the minimality of delta, or local minimality of delta, one gets enough iterability for collapses of countable elementary submodels of LV delta, and this by pretty much by classical theory of iteration trees from the 80s, Martin Still. So we end up with an iteration tree T in N by pretty much following the approach that I gave before, not literally, but in spirit, it's essentially that on M. So you build this, you end up with an iteration tree T in living in N of length, successive length, such that the last model is well-founded at least up to delta star. That's the image of delta. So we don't necessarily get well-founded for all of it, but at least up to the image of delta. And again, this set is generic for its extended algebra. So for this to be, in order to carry out this point 2, we need the countable model N to be such that N of H is sigma 1,3 correct in V, and this for any generic extension of N. And that's why I want the proper class of Woodin kernels. So, and we get that if N is a collapse of a suitable countable and an elementary submodel, thanks to the existence of a proper class of Woodins in V. Okay, so this motivates sort of cheating notion of omega logic, where you say, okay, which talks not about set generic extensions, but something slightly more liberal. So you say that you have models W and M, And you see that M is a one-step local forcing extension of W. In case there's some ordinal delta in W, such that M is a set forcing extension, not of W necessarily, but L of V delta in W. And then you iterate that, right? So you can say, given an N non-zero, M is an N plus one step local forcing extension of W. In case there's an N-step local forcing extension M0 of W, such that M is a one-step local forcing extension of M0. And you can say that M is an iterated local forcing extension if there's some N such that M is an N-step local forcing extension. Okay, so now you could define local omega logic with respect to this set of models. So I have a set T of sentences and sentence sigma, and then you write that T follows from sigma in this weaker logic in case for every iterated local forcing extension M of V and any alpha, if V alpha, if this model satisfies C, then it satisfies sigma. Okay. All right, so a variation of the proof I mentioned before gives you that a completeness theorem for this weak version of omega logic. Okay? So suppose there's a proper class of Woodin cardinals and let sigma be a sentence, then the following are equivalent. Sigma is valid in this logic. And if delta is any ordinal, such that delta is Woodin in L of V delta, and the set of Woodin cardinals in it is bounded in delta, then it thinks that sigma is valid. Yeah? In this logic, and then there's a real R such that for every countable transitive model N of Z of C, if it contains R and it has sigma 1,3 correct, every extension of it is sigma 1,3 correct in V, then N will agree on this thing. And this N, for this, so think of N as containing M transitive collapse of elementary submodel of this guy. Okay, so you have these equivalents, and from 3 you get this corollary that if there's a proper class of Woodin cardinals, then the set of validities in this logic is a sigma 1,5 definable real. All right, so this was motivated by this extended algebra approach to the omega logic. And now I want to mention something about honest consistency, which is also an idea motivated by omega logic, okay? I'll start with a theorem that Ben mentioned in his talk by R Schindler that, okay, so suppose N is precipitous, then given any kappa, at least omega 2, there's a stationary preserving force of posed P, which forces the existence of a countable model M and a generic iteration in the sense of iterations by this ideal. Okay, I'm going to define this such that the last model is H kappa V, right? So you are making H kappa generic from a countable model. And the proof involves showing that there's in some outer model, that there's an outer model W in which the above situation holds, this conclusion holds, and every stationary set of omega 1 in V is stationary in there. And using this fact to devise some sort of forcing by approximating sentences of with side conditions, which will preserve stationary sets, that's why you have the side conditions, and will approximate this embedding. So that's the main idea. Okay, now in some situations, given a suitable outer model of W, which satisfies maybe some sigma 1 statement of interest, and such that every stationary set of omega 1 in V is stationary in that outer model, we can devise some recursively defined L forcing P, I don't want to say what this is, with side conditions again, which will preserve stationary sets will approximate a generic iteration that of like the one in the previous slide living in W, and moreover, which will approximate W. Okay, this is sort of a difficult part.
In what sense does it approximate?
Oh well, I mean, it will force the existence of some model which satisfies your sigma 1 segment. That's what you want. So using this approach with R Schindler, we proved that an M double plus implies star, and the proof proceeds by showing this axiom that there is a suitable W, okay, in the relevant sense, and then you continue as in the previous slide. So so now in particular, the forcing P in that proof makes the H omega 2 of V the final model of a generic iteration, right? Of some countable model M. So it forces that P forces that the coffinality of omega 2 V's is countable. In fact, the pointwise image, the pointwise image of V omega 2 of M is countable is cofinal of V. So it's like lambda force, right? Okay, so this is now this can be somehow generalized. And okay, and for this, I want to motivate this generalization. I want to talk about some fragment of and then double plus, which is well given which okay. So take a cardinal lambda, and then BMN double plus, and I got this cofinality omega. This less than lambda will know the following. We'll take a kappa less than lambda, an X is H kappa plus, and take some sigma 1 formula in this language, and suppose there's a seizure set forcing the statement, and moreover, which makes every cardinal mu between aleph 2, aleph 1, and to kappa omega cofinal. Okay. Then in V, then you can reflect this out. Right? So in V, you have lots of sets, and which such that such that the collapse of X will satisfy the formula in this direction. The conclusion you would get from an M double plus. Okay. Now, right? So naturally, just natural strong form, bounded form of this strong forcing axiom, and then just for number forcing and things like that. Right. Now, what we can prove is by extending the proof of, so by a variation of the proof that MN double plus implies star, we can give the following enhanced form of this forcing axiom from MN double plus. So, all right. So what we get is that, okay, so suppose MN double plus holds, and now take some kappa less than aleph omega 1, and we need this. We need kappa to be less than aleph omega 1. So now take an X in the H kappa plus, take a sigma 1 formula as before for this structure, and suppose that somewhere there's a transitive model W, which is sufficiently close under this sharp operation, which contains H kappa plus of V, also has a Woodin kernel of this ordinal, and okay, so this is much about correctness, and then it's also relative, it's also natural substitution. It says every seizure is set of omega 1 in V is seizure in W. Then I need this extra thing so that it makes all of these V kernels omega final and satisfies the state. So in this situation, I can find in V, also I can reflect this statement. You have lots of hands where this holds. Okay, so this is what we can prove, and then well, okay, so there's all right, so there's this natural notion of being a statement being not consistent, but consistent in a nice way, honestly consistent, which says that well, that happens in case for every universally bare set A, so this is like in omega logic, there's an A closed transitive model W of Z of C star in some outer model, which doesn't destroy stationary sets of V and thinks that the statement holds. Okay. So this is pretty much like what you get in the context of omega logic, but moreover, you have this niceness property in one. All right, and then you can define MM double plus star to be the same that if you have a sigma one statement which is honestly consistent, then it reflects down to V. Now, the previous theorem shows that a natural fragment of this very strong form of MM follows from MM double plus, but this question still remains open. So is this strong form of MM double plus consistent at all? Is it maybe equivalent to MM double plus? It's not known. Okay, and right, just my last slide is that you could maybe hope to, it's not news, it's, you could maybe hope to want to prove the omega conjecture by something like this, some L4C, right? But that looks hopeless because, all this, you would maybe conceivably, you will want to approximate some outer model W, which thinks maybe with extra properties, which thinks that some things, this sigma holds in some V alpha, but then, you would get a generic model W which satisfies this, but the forcing extension has a lot of, much more stuff in its V alpha. So, so that's why sigma 2 statements don't work, but sigma 1 statements do. Right now, compare this with the situation what we had in the external algebra approach, where we managed to get equality here. That was crucial there, and so that's all. Yeah. Oops.